Alrighty, so this is a buck converter I designed. What it does is it steps down 24 volts all the way down to 5 volts and can supply up to 1 amp of current. So what I'm going to do in this project series is I'm going to take you through the entire process of designing one of these, basically from idea to manufacture. But before I go any further, please remember to drop a like on the video for me. It helps my channel out tremendously. And if you want to stay up to date with more videos, the rest of the videos in this project series, then hit the subscribe button for me. That'll also be super helpful. So yeah, what I'll do is I'll share with you things like right now we're looking at like the PCB layout. So I'll go through the entire layout steps. I'll share with you all of the details. I'll share all my like layout notes with you. We'll look at the circuit design. So we'll take a look at the schematic and I'll kind of explain. I'll teach you everything I think you need to know about the schematic. And then we'll do a bunch of component calculations. So I have a whole bunch of component calculation notes that we'll go over. And then there also is a little section here where I'll teach you about like the specific chip that we're using, which is the LMR 14010. So that's just the buck converter chip that we're using. So yeah, that's pretty much all the stuff I'm going to share with you for this project. And then let's just go over some of the quick project details, I guess, as well. So some of the main project details, like I mentioned, is we got an input voltage of 24 volts. I think I put the range around 22 to 26 volts. So kind of what we're expecting here is, say you have a typical, brick external power supply that supplies 24 volts, and usually that has like in most cases you will definitely never see anything less than 22 or anything greater than 26 out of a well-designed external power supply. So that's the range I have our buck converter being able to operate from. Then our output voltage is going to be 5 volts. I think we're going to shoot for a ripple voltage of around 1 to 3% on the output. So that's like 0.05 volts all the way up to 0.15 volts on the output. And then we have designed this buck converter to be able to supply up to 1 amp of current. So that's what a lot of our components are rated for. And that's what our design is around. Here I have both an input and output connector specified for this project, just for the sake of learning more about connectors. I chose 2 Molex connectors. I'll just point them out to you on the board. So this is one of them. Obviously, I really like picking connectors, especially for these types of projects that have really good step files for them, because just aesthetically they look much nicer when you go to 3D view of the board. And then this right here is supposed to be the other connector. So this was actually a right angle connector. And I mean, as you see, the 3D step file that came with it is just a block. So what it really happens is this is just, and we can look at the bottom side of the board here. So you have some anchor points. So you have our 2 actual contacts that can make connection with the circuit, and then you have this little anchor point that supports the actual connector, because as you know, you're plugging in and unplugging this connector, so it's going to have a lot of physical torque put on this these joints. So you don't want all the force and torque being put directly on our electrical connections. You want to try to distribute that across some other non-critical connections. So what this is doing is this actually is a right angle connector, and it sticks out a little bit over the board. And then this is just a regular old vertical connector. They're 2-pin connectors, so you're just power and ground, and then so one's going to be like the input for 24 volts, and the other is going to be outputting 5 volts. So that's kind of what we have there. Then I have a couple of miscellaneous details. So I say it requires at least 1 mounting hole size to work with an M2 screw. So we end up going with 4 mounting holes, as you see on the circuit, and then right here. And this is a pretty good thing to actually get into practice doing, because pretty much all PCBs nowadays have mounting holes on them. There might be some rare circumstances where they don't have mounting holes, but I mean, the reason why you have mounting holes is, of course, is because you're usually almost always mounting these PCBs in a protective case that requires some screws just to fasten it to the inside of the case so it doesn't rattle around places. So getting used to designing boards that have mounting holes on them is very useful and it's a regular thing, so it's good practice. And the other constraint I try to put on this is just make the board as small as possible. So this is obviously something that a demand that will get quite often, is it needs to be as small as possible, where you're usually trying to work within, you always usually have less space than what you think you need, so you always have to try to shrink things down. So that's kind of just a constraint I put on this project as well. So yeah, that pretty much covers it for all of the details I want to share about this little intro section. So what I'm going to do is I'll section out the rest of the videos. That way I can go in deep dive into specific sections. I'm not sure how many parts this video is going to end up being. I know our component calculations, I have a lot of notes I want to share there, so I probably will break that up into multiple sections, and then I will probably break up the circuit design notes where I'll go over general circuit design like tips and a breakdown of the actual circuit as well, and I'll probably break that down into multiple sections as well. So I'm not really sure how many sections it's going to be, but as you know, that's how I usually like to structure my videos on this channel, at least right now. But that pretty much about covers everything I wanted. So yeah, like I said, if you have any questions about this, drop a comment below and I'll be happy to answer it. Any project ideas you got, also leave those in the comments below, and I will add them. I have a huge list of stuff. Maybe even for the rest of the year I have stuff planned out. We'll see how long it takes me to get through these projects. But yeah, so yeah, that's pretty much all I have to say in this video. So thanks for watching. Hopefully I will see you in the next one. Video, I'm going to be going over the circuit design for our buck converter project. So we'll be taking a look at this entire schematic, and I'll be just breaking down all of the important parts of it, kind of explaining how everything works, going over some of the functionalities of some of the little like subsystems in here and stuff like that. I have a little circuit design notes page that we're going to be following along with that has some important stuff on it. And so yeah, but before we go any further, please go ahead and drop a like on this video for me. That helps my channel out a ton. And hit the subscribe button as well if you'd like to stay up to date with any of the future videos in this project. So with that out of the way, let's just jump right into it. So the first thing I have here on my little design notes page is U1, which is our buck converter IC. So U1 is this little yellow square right here with all these little pins, and so pretty much modern electrical engineering and modern circuit design is built around a lot of these little things you call like chips or ICs, which is short for integrated circuits. And they're a bunch of like semiconductor based circuits with a bunch of like transistors and processing units and processing systems inside them to kind of run our circuits for us. So think of this thing like a little bitty computer with a bunch of little inputs and outputs, and we're basically trying to program this computer with some other hardware components, which are what you kind of see as all these resistors and other things like that. So yeah, so first bullet point up here is its job is to monitor the input and output voltages and control the current through the inductor. And I think that's a good segue into the fact that, so whenever we look at this circuit, you're probably wondering, okay, this doesn't look anything like that typical buck converter circuit that if you've actually watched my buck converter basics video, which will be linked in the description by the way, you're probably like, okay, this does not look familiar at all, so what gives? And so actually let's just go take a look at that. I think that's a good starting point. So buck converter basics, so this is the circuit that I introduced and said, okay, this thing is a buck converter. And so this thing is actually like what is responsible for stepping a higher voltage down to a lower voltage, and you're like, okay, but this doesn't look anything like this. So I think what we could do is let's just go through our schematic, and we'll start pointing out all the little components that are present in our buck converter basics, in our what I would call our fundamental buck converter circuit. And that'll be a good starting point. That way we have some familiarity with what's going on here. So let's just start with the first one, which is going to be L1. L1 actually corresponds to L1 in the circuit. So this is our little, what do you call, output inductor or power inductor, which is kind of what the whole circuit is kind of based around, which is controlling we're trying to control the current through this thing. And like I said, that's what this chip is doing. Then we have D1, which is our rectifier diode, which connects this end of the buck converter to ground, kind of like I said, whenever the current loop is flowing just in this direction, right? And so that's what this little diode is here for. So it's doing the same thing. So here's our ground point, and then here's the inductor going through the rest of the circuit. And then we have, let's go up here, let's take a look at for our output capacitor. That's what these things right here are. So right here we have 3 quote-unquote output capacitors, and I'll explain what they're all doing in a little bit. But just consider these are little output capacitors which do like the job of like smoothing and stuff like that. And I'll explain exactly what these do later and why we have multiple of them. So continuing on with this, so we have, let's look, we'll find our input capacitor, which is this C2. This is our input capacitor. And you're probably wondering, okay, so now things look familiar, but hold up, you totally forgot one, and that is where's the MOSFET? You know, that's kind of an important component for this buck converter circuit. And I think here, let's just take a look at it, back to the circuit design notes. And if you look at the second bullet point, it says that U1 has an integrated MOSFET, which is why we don't see one in the circuit. So this yellow box, which is our little chip, which is this tiny thing right here, this has the MOSFET inside of it already. It is integrated into the chip. So we don't actually have to go and pick one when it comes to designing our circuit. It's already provided for us, so it just makes design a little simpler and more efficient. So it's like the whole point of that. The downside with this is if you have like a very, you can't be very, it's not as flexible of a design, right? Let's say you need a really high power rated MOSFET for some reason. Like say you're trying to provide like 5 amps of current for this buck converter. You can't do that with this chip probably because the MOSFET is likely not rated high enough. And we'll take a look at the data sheet later and see exactly how the inner workings of it work. But yeah, so that's just kind of one thing we're trading with this chip is that we have a simplified design. However, we are less flexible with what we can do with it. So it's, you know, this works a lot with I mean, the reason, like, this is by Texas Instruments, and the reason they make that is because there's obviously a good demand for chips that can do simple things and help with the simplicity of design, but then lack flexibility. So it's not like it's a good trade-off. So yeah, so let's go look at the next thing. Let's take a look at the input side of our circuit. So like I said, starting at the left, so here we have our input connector, which is a Molex connector, and here's the part number for us. So it's just a 2-pin connector. Let's just double click on it and we'll take a look at it. So input connector has a voltage rating of 600 volts and 8.5 amps. So those are the 2 biggest things that I looked at whenever it came to picking these connectors, or just their voltage and current rating, and the fact that I knew it needed just 2 pins because we have a power and a ground pin, so it's not like we're sending signals or anything like that. So yeah, like another consideration you might have for a connector is, well, there's actually a lot of, like, connectors actually are a lot more, the considerations tend to be a lot more mechanical than electrical, in the sense that you could probably find a lot of connectors with an appropriate voltage and current rating. I mean, this is a tiny little connector, and it's rated for 600 volts and 8 amps, and this thing is super small in terms of, like, if you were to go and that's one thing I'm actually kind of getting to, is the physical size of the connector matters in this case, because say like maybe this connector was getting plugged in and unplugged a whole bunch for whatever reason, you might actually go for a bigger connector because it might be easier for a technician to get their meat paws in there and plug things and unplug them. But if this is only going to be plugged in during assembly, like it's only meant to be plugged in like once or twice throughout the lifetime of the device, then, you know, and maybe you need a really small form factor case, then you might go for a smaller connector. You kind of see what I'm talking about here, is that, so that's probably why we'll start featuring a bunch of different connectors in our projects. That way you can get a good feel for understanding the variety of connectors are out there and the options you have to play with. But that's just one thing I want you to kind of keep in the back of your mind when it comes to thinking about connectors, is what are all of the things that this connector is going to, what's the environment that this connector is existing in, and what are things like how many mating cycles you could think about. That's a good stat, is how many times is this connector going to be plugged and unplugged in, and who's gonna have to be doing it? Is it like your typical like consumer? Like think about like an iPhone charger. They're plugging in and unplugging that thing in a lot. So maybe you want to make that appropriate for, you know, the average bear to be able to plug and unplug, something like that. So those are just some considerations. And I kind of had the same thing for the output connector, is the same exact considerations. I mean, we look at this, we have a same really high voltage rating and current rating. And so it's super easy to find stuff that is appropriate. Now this one is a right angle connector. I just wanted to put that in there because it is just so that we know that those exist and those are like an option for us. And one thing I want to touch on real quick as well, with when it comes to choosing between a right angle and a vertical oriented connector, one thing you also have to think about is the conditions under which this connector is like applied to the board. Again, going with the environment that this connector exists in. So let's say I'm unplugging and plugging this connector in a lot. How would I say this? So think about this. We have this board that is supported by 4 mounting screws. That means it's going to be laid flat on the ground, and it's going to have really strong support in the we'll call it the Z axis, the up and down axis, because you have these 4 strong mounting screws that are holding it placed up and down. And the same thing goes for a vertical connector. Has this huge surface area to distribute any type of torque or force across the connector, right? We have this huge flat surface underneath us supporting us, so anyone plugging it and unplugging it, versus our right angle connector. If you're like plugging in and unplugging in sideways, you have a lot less area for that connector to exist in. So kind of what I'm saying is a vertical connector has a lot more like support, a base of support for like when you go to plug and unplug it in. So it's probably not going to it's going to be more resistant to like breakage and any sort of like damage to the connector if you're unplugging and plugging a lot. So it's a safer bet generally to go with vertical if you can. But again, with form factor, and there's a lot of other constraints to consider, that's what I just want to point out, that right angle connectors exist as well. So I think that's going to be a good spot to stop for this video. The next part we'll probably get into the rest of the input stuff. I'll kind of explain some of these little notations here on our schematic. We're just going to start working our way from left to right, I think. So thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Okay, so we're going to be continuing on with our circuit design notes, and I'll kind of be going over again more of the details related to everything we see on the schematic here, and I'll kind of explain how what's going on here. Before we go any further, please go ahead and drop a like for me on this video. It helps my channel out a ton. And subscribe if you want to stay up to date with any of the future videos in this project series. So with that out of the way, let's just jump right into it. So previously we talked about the main star of the show, which is U1, which are like converter chip, converter IC. And then we kind of got into the choices of our input-output connectors. And now we're just going to start working our way through the rest of the circuit. So the first thing I guess I want to point out here is this little, in Altium they call these like power bars, I think, or it's a bar, but it's a power port. There you go. So these are power ports. So ground is a type of power port as well. This is to symbolize V external. This is just for connectivity reasons. But this is supposed to represent the external power supply that is coming from, you know, whatever we're plugging into our board. In this case, it's a 24-volt power supply. It's just gonna be like, in my head, I envision like a brick being plugged into our board, and then that's where we're going to be bucking into to our 5 volts. And then of course we have our ground power ports, which I just have throughout the circuit wherever it's necessary and stuff like that. So yeah, let's just check my schematic notes and see what we got next. So next thing is we have a voltage divider on the input side to send the chip into under voltage lockout whenever VN falls below a certain level. So that is what this is. So what we're doing is V external, we're taking 24 volts and we're dividing it down to a certain value, and then we're sending it into this shutdown pin. And that's what's going to do, is going to send our chip into under voltage lockout mode whenever the voltage gets too low. Don't worry, in a later video in our component calculation section, I'll explain exactly how I picked these two values. And then in another section where I explain the inner workings of this chip, I'll explain what the shutdown pin does. But no, that's just what's going on here, is that this is a voltage divider. So we're just voltage dividing 24 volts down to some voltage number. And that's what's going on here. Then we have our input capacitor right here, which corresponds with this little Cin right here. And I will also, in the component calculation section of this video, or a section of this project, sorry, I will just go over exactly how we picked this value and some other important parameters associated with our input capacitor. So that's what's going on here. So we have our 24 volts being filtered by this input cap, and then we have it being also sent into the VN pin right here. So it's being input into our VN pin, but then it's also being divided down into our shutdown pin to control whenever we go into under voltage lockout. So I hope that makes clear sense here. Then just continuing on, so CB, this is our bootstrap capacitor, is what this thing is known as. And what the bootstrap capacitor actually does, and this will make more sense whenever we go into the inner workings of this chip and understand what's going on inside it, but what the bootstrap capacitor does is it actually supplies the voltage that is necessary to switch our MOSFET on and off. Now, if you watched I actually have a lot of videos on the channel that could pertain to this. If you watch my MOSFET gate drive circuit video, you'll understand that MOSFETs are voltage driven, and so you need a certain voltage at the gate pin in order to cause the MOSFET to conduct. You'll understand that if you watch any of the flyback converter projects, you'll understand that that is what the output pin of our flyback converter does, is that it supplies a voltage to the gate pin of our MOSFET in order to allow the MOSFET to conduct to control the current through the primary winding, right? So in this case, we're using a capacitor to supply that voltage, because you can think of the capacitor like a battery in this scenario that is holding up some charges for us, and then we're just drawing from that battery at a certain time whenever we need to drive the MOSFET high or low. And it's actually an ingenious, when we look at the inside, you'll see what's going on there, but it's actually an ingenious design feature that whoever thought of that is brilliant, I think. And it increases our efficiency a whole bunch, because if you have like a battery, you charge it once, and then since MOSFETs use very little current, this capacitor can work for a whole, it can be used to drive that gate pin of the MOSFET a whole bunch over and over and over without drawing much current, right? So it's a really elegant solution here. So then continuing on, I already covered, we know this is L1 and our diode, or we can call it rectifier diode, which just controls the current, that one-way directional connection to ground, so it allows the current to flow this way through ground whenever the MOSFET is no longer conducting. And then we have our power inductor, which is the whole star of the show. We'll start the show behind U1, of course, which is the one supplying the power, which is the one it's the thing that we're using to allow the current to ramp up and ramp down to our desire. Then continuing on to the right, we have another voltage divider. So what this is doing is this is a voltage divider. So this is our output. So if you scroll, look away, looking forward, we have 5 volts, 1 amp. That's what this line is sitting at, is 5 volts, 1 amp. Right. So wherever you plug into this right here, this is going to supply 5 volts and up to 1 amp of current to our whatever it needs, right? This could be many different things that need 5 volts, 1 amp. I mean, this could be an iPhone charger, honestly. So what this line is doing, though, is it's monitoring the voltage right here. So we have a voltage divider, so it's taking 5 volts, 1 amp, and it's dividing it to a certain value, and that's being fed back into the chip. So that's one of the inputs, one of the 2 inputs we have into our chip. Remember I talked about how the chip is like a computer that takes some inputs, and it's doing a bunch of computations and running basically a small little very simple program on the inside of this thing that is controlling the switching behavior of our inductor, right? So if the voltage is too low here, then we're letting the current through the inductor ramp up a little more. The voltage is too high, then we're shutting the inductor, we're opening up that switch right away, right? So this is going on. So this is just a way for us to monitor the voltage line right here directly without drawing too much current. Because if you see this, we have sorry, I forgot what I was saying. If we're this is like a huge amount of resistance here, so we're not drawing very much current. It's being fed back to the feedback pin. So then continuing on here, so now we're looking at our filtering capacitors. So what we have here is, this is our main, we call it rectifying or smoothing cap, which is like the 22 microfarad capacitor. So this does all of the primary smoothing job for our circuit. And then the other two caps, and actually, yeah, this is, so it's a 0.1 microfarad and a 0.01 microfarad. So the reason I threw these on here is to just filter out any of that higher frequency noise you might have on these capacitors, so, or on this 5-volt line. So what you'll do is, the way you kind of think of these capacitors is just their ability. So the higher or the lower the capacitance, the better it is at filtering high frequency noise. So you think of, I look at these as having individual jobs and not as like summing to one capacitor. So for example, this capacitor might be really good at filtering noise like the 10 kilohertz range. Well, this one might be better at filtering noise in the 100 kilohertz range. So we're just kind of dispersing out our ability to smoothen out this line and take care of any of the higher frequency noise. So that's kind of what's going on there. And then I have another power bar that is 5 volts. So it's just to denote the 5 volts of the circuit right here, and just have a nice net name for that. Then we're feeding into our output connector. So yeah, then the last thing we have here on our schematic is going to be our 4 mounting holes, which correspond to these things on here. So in this case, the mounting holes, I just made them a component in Altium. And so they have their own footprint, if you see right here, and then they have like a little schematic symbol. And the reason for that is because sometimes you want to ground your mounting holes depending on what they're connecting to and where they are located on your board. And so I just did that to show that, yeah, so we have our 4 mounting holes and we have them all connected to ground. And that is pretty much the gist of what's going on in this circuit. Like I said, we'll get into some very specific values on how I got all these and other parameters that are important. So yeah, if you have any questions, then go ahead and drop a comment down below and I'll be happy to answer it. If you have any project ideas for me, then drop that in the comment section below and I'll add it to my list of stuff I have. So yeah, thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. In this video, we're going to be going through the datasheet of the LMR 14010A. So I'm going to be kind of covering a bunch of the details, showing you the inner workings of the chip, and kind of teaching you about how these things work in the context of our circuit. But before we go any farther, please go ahead and drop a like on the video for me. It helps my channel out a ton. And subscribe if you want to stay up to date with any future videos in this project series. So with that out of the way, let's just jump right into it. So I have this little note sheet that I kind of want to go through that's going to take us through the different sections of our LMR chip, and I'll just kind of go through the data sheet and give you some helpful info about it. So first thing we'll start with is some summary and background. So this kind of chip is called a converter. And so if you go on TI's website and you're looking around for buck converter chips, is what you call them, buck converter ICs, you'll see there's two main sections. You'll have a converter or a controller. And the main difference between a converter and a controller is going to be the integrated MOSFET that we talked about earlier on when we were discussing our circuit design notes. I mentioned that the reason we don't see a MOSFET on this circuit is because it's integrated within the chip. And I mentioned the reason we do this is because it simplifies the design for us, makes it a little faster and easier at the cost of being less flexible. and we'll see where that comes in later on when we talk about the description, is because since we have the MOSFET is basically already chosen for us, we can't modify it in order to fit any type of certain designs this chip will not work for. So yeah, the other bullet point I have here is basically, and I kind of covered this earlier on, but we'll just reiterate, is the LMR 14010A is basically a very simple computer that monitors the input and output voltage and controls the current through the inductor. So its entire job is to just switch on and switch off that MOSFET in order to control the current through the inductor, in order to create the output voltage that we desire. So taking a look at our buck converter basics schematic, its job is to just flip this switch. Remember when we talked about you have the two states of where it's conducting versus when it's not conducting. Its job is to decide when it's supposed to be conducting and not conducting in order to give us the desired output voltage. All right. Let's see. So the next thing is here, we'll take a look at the description section of our chip. I'll keep calling it chip of our LMR chip. And I'll kind of point out the things that I think are important for learning whether this chip will work for your design. So the first thing that kind of stood out to me in the description section was the input voltage range. That's a good thing to check to see if it'll work for your design. And so notice it says we have a 4 volt to 400 volt input voltage range. And that's kind of interesting because it has a minimum input voltage range, right? So you can't buck 3.3 volts down to 1.7 volts or something like that, right? It requires at least a VN min of 4 volts. And I think the reason for that has to do with the driving of our MOSFET gate pin, because if you know MOSFETs are voltage driven. In order to have a minimum, in order to get them to conduct, you need a minimum voltage, and so we can't achieve that voltage level if we have below if we're below 4 volts. If hopefully that makes sense. And then we have a maximum of 40 volts, and that's just going to be various components could be rated at values. There could be logic transistors, and there could be some internal capacitors or something like that that are just rated at 40 volts. And so that's why you can't go over 40 volts. So that's an important thing to pay attention to make sure it'll work for our design. And since we know our input voltage is 24 volts or maximum is 26, then this will work just fine for our design. The next thing that kind of to pay attention to is that this is a fixed frequency converter. You have typically with our converter chips, we'll have fixed or like variable frequency. Meaning like you can either set the frequency with like an external resistor, or the frequency could change on its own depending on a number of circumstances. But yeah, so this frequency is fixed at 0.7 megahertz, so 700 kilohertz. This kind of matters in the context of understanding the impact to electromagnetic interference that our chip will provide or cause. As well as just understanding maybe some of the other components and how and their frequency response range in terms of like inductors and capacitors and stuff like that. So it's not too crazy. It's not too critical, I guess I should say, understanding this value, but just know that it's fixed and know it's at 700 kilohertz. So the next thing in our description here is that is optimized for up to 1 amp of load current. So technically, I guess I could go over 1 amp of load current, and I think we'll find it in the absolute maximum rating section if we just check our this section of it tells you the maximum absolute ratings, and it should give us a current rating. If not, so yeah, I think current rating is probably in here somewhere. But if not, then just know that it's optimized for up to 1 amp of load current. Just know that we don't want to be drawing more than 1 amp of load current with this thing. That probably has something to do with our MOSFET's current rating. The last point in the description is that we have a 0.765 volt nominal feedback voltage, and this will come into play whenever we are talking about that voltage divider that goes into the feedback pin. And we'll see more about this 0.765 volt nominal feedback voltage whenever we go look under the hood and check things out in terms of like the inner workings of the chip. So that's pretty much everything for the description section. And then moving on, we will take a look at what is the next thing I have on my notes is the pin functions. And this will, let's just take a look at those right here. So pin functions. Right here we go. So I just have this little table here, and I have these little notes. So pin function. So pin 1 is the CB, is named CB. This is the bootstrap capacitor pin. So this is the switching FET gate bias voltage connect C boot capacitor between CB and SW. So that means these two pins. If you scroll up and look at our application circuit, that's what it's talking about. We have a bootstrap capacitor here between our switch pin and our CB pin, and we'll see more about that whenever we look under the hood later on. And I talked about this already about what the purpose of that is. I talked about that in the circuit design notes about how its job is the bootstrap capacitor's job is to supply the voltage that we need to drive the MOSFET, and we have the internal logic switches that are controlling whenever we're actually using that capacitor voltage and when we're not. It's pretty ingenious, I think. So the next pin that we're going to take a look at is the FB pin, which is pin 3. This is feedback pin, set feedback voltage divider ratio with V out equal to VFB times quantity 1 plus R1 over R2. So this is our first little formula for designing the feedback section, this little voltage divider here. This is what it's talking about. We have R1 and R2. This is R2 and R4, but just know it's talking about this. So it's telling us how to pick these two values and send those into the feedback pin. It even gives us a nice equation for understanding like what V out is. And we'll take a closer look at that in the component calculations section of the project. But no, that's kind of what it's talking about. Then we have G and D, which is our ground connection. Pretty self-explanatory. You just tie this one to ground. And then we have shutdown, which is, so the thing I want to note here, shutdown pin. So this is the under voltage lockout pin, meaning, so what happens is if say for some reason this voltage fell below a certain value that I've set here, if the shutdown pin voltage falls below a certain value, then the buck converter will just stop working altogether. And this is done for like circuit protection, and there's a number of other reasons. You could just do it because you don't want for like efficiency reasons, or you can do it as a controlled just behavioral decision that you want. Say this is supplying voltage to another, say this is just supplying voltage as like a signal or something like that, then you just want to use this as a way to control that, if that makes any sense. So enable to disable input, internal pull-up current source below 1.25 volts to disable. So that means if the shutdown pin falls below 1.25 volts, then the buck converter will just stop working altogether. So it just says adjust the input under voltage lockout with 2 resistors. So that's kind of what we did here. So we have a voltage divider feeding into our shutdown pin. So we're dividing 24 volts down to a certain value in order to set when our under voltage lockout condition occurs. So and then this other thing I want to note is, so this bar right here, this means active high, meaning that whenever this pin is quote unquote high, meaning above 1.25 volts, that means the circuit, the buck converter is working normally, and whenever it's low, that means it's inactive, meaning that's what causes the pin to shut down, or that's what causes our converter to shut down. The SW pin, which is our switch node, connect to the inductor, diode, and C-boot capacitor. Pretty self-explanatory right there. So this is actually like our quote-unquote output pin. This is where all the current flows, and this is where we control the current through our inductor. So it's pretty simple there. And then we have VN, of course, which is the power input voltage input for internal supply and drain node input for the internal high side MOSFET. So we'll take a look at what that is, what's going on there. and when we look under the hood as well. But this is just like what we attach our external voltage or our VN pin to, right? So this is the input voltage, and this is the like output voltage. So this is where 24 volts enters is the VN node, and then it exits as 5 volts, or I guess I should say it exits as 5 volts. It's 5 volts when it gets all the way out here, and we'll kind of explain that a little more closely. But yeah, because it definitely probably wouldn't be 5 volts at this point right here. And if you understand how like buck converters work, then when in my video I explain what's going on there. But yeah, just understand this is just the output voltage right here. So yeah, that's pretty much, I think that's a good stopping point for this video. In the next video, we'll be going on with the rest of this, taking a close look at the functional block diagram. There's a bunch of notes I have on that. So yeah, hopefully I'll see you in that video. Okay, so we're going to be continuing on with the breakdown of our LMR chip and understanding like the internal workings of everything that's going on in this chip and kind of how it behaves and works. But before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton, so I'd really appreciate that. And subscribe if you want to stay up to date with any future videos in this project series. And so with that out of the way, let's just get right into it. So the next part of our data sheet that we're going to be taking a look at is going to be the functional block diagram. So this is going to be a pretty complicated section of this. So I'm going to go through it nice and slow, and we'll kind of step through all the important parts for understanding how it works. So let's just take a look here at our functional block diagram. So yeah, let's just see what I have here on my notes. So the first note, so the feedback signal is fed into an air amplifier and compared to a constant 0.765 volts. The 0.765 volt signal must be very low current. I guess, so the reason I put that is because what's a little bit of a mystery and probably a sort of a trade secret is how they achieve a constant 0.765 volt signal, because you're probably wondering, well, if you can create a 0.765 volt signal no matter what the input current, the input voltage is, why can't you just do that and just put several of those 0.765 volt signals in series to add up to our, whatever we need it to, right? Our 5 volts or whatever signal, right? And then you could just simplify this circuit a whole bunch. We don't have to put a bunch of inductors or anything like that. And so my answer to that is probably because it's a very low current capability signal that they have right there. But the main point to understand here is that looking at our circuit, right? So we have a voltage divider being fed into our feedback pin, right? So what you kind of imagine is that what we have is a voltage that's, imagine it's starting at, say we just fire up this converter, and so we are slowly ramping up to 5 volts, right? So say this signal is 1 volt and it gets voltage divided down. And so say it's like 0.1 volts or something, or 0.02 volts. Whenever the VCC line right here is 1 volt, say pretend this signal is like 0.01 volts or something. So that means we have going in here, we have a 0.01 volt signal being compared to our air amplifier. So what's going to happen is that this signal is going to be pulled high, just like a regular old op amp would. Whatever the high rail is, it doesn't say, but then that is fed into more logic. So basically what it's kind of saying is we're flipping between two modes. Is we know whether our signal is above 0.765 volts or below 0.765 volts. And based on that, it sends a certain signal into the logic portion of our circuit. And so that's where all the computation happens. And so I'm guessing it's going to say something along the lines of, okay, feedback signal is below 0.765 volts, then turn on the MOSFET. That means let the voltage continue, let the current continue to ramp up until once it gets higher, then we're gonna flip it off. We're gonna switch down, or we're gonna no longer let the MOSFET conduct, right? And then the voltage is gonna start going down, and we're just gonna keep doing that really, really fast. And that's kind of what the whole logic portion of this circuit is doing right here. So that's kind of where we get the 0.765 volts number from. It's because that's what we're comparing it to, and that's why we pick a voltage divider to send into our feedback pin. And don't worry, we'll go over how the exact equation and the rest of stuff for picking our values for our voltage divider in component calculation section. But I just want to know that's kind of what's going on in this section of the circuit, is that we're feeding our output signal into a air amplifier, and that's kind of what's going on in this section of our circuit. So the next thing is SS. Yeah, I just want to comment on what, if you looked at the data sheet, we see SS, and that stands for soft start. And so something I think it was in the description or the beginning of this, it says internal soft start. That's where that comes from. And we talked about what soft start does. If you watch some of my other project videos, there's some chips that have soft start functionality. We even had to program one. I say program, we had to put some hardware components to set up our soft start functionality for this circuit. But yeah, so that's kind of what that is doing as well. Is it's just controlling like the duty cycle and causing it to slowly ramp up. But that's what that means. And so we're just trying to mess with the signal around this area. So that's kind of all that's going on here. It's not, you have to read too much into it to understand what's going on here. So then the next thing I have here is see how the MOSFET gate pin is controlled. This part is really cool to me whenever I was first reading this chip and learning how it works. So let's pay attention to the MOSFET gate pin. It's controlled by the high side driver, right? Now remember what we've talked about, and if you're familiar, so I've featured MOSFETs on this channel several times, understanding how they work and stuff like that. So I'm not gonna get too much into it, but just the thing I want you to remember is that MOSFETs, like I said, they're voltage driven, and usually they take about 5 volts or more, maybe 10 volts, in order to allow them to conduct. And so you're probably wondering, well, where do we get all that voltage from? Right, especially if we're trying to create an efficient converter right here, then obviously we could get it from VN, but that could also be too high, right? Like VN could be 40 volts, right? That's what this converter does. So the genius part here is, okay, so HS driver, high side driver, this is an op amp as well. So what you want to look at here is that, so it looks just like an op amp. You have our input here, and this is just a simplified input. But then you have the high side rail, and you have our low side rail. So if you remember how op amps work, is that whatever their input, based on the input, they're either getting pulled to their high side rail or their low side rail. And so basically what we're doing, and look at the pin that's feeding into this, is the CB pin. So how do I break this down? So like I said, we're either toggling between the high side rail or our low side rail here. And what our high side rail is remember, imagine the CB, this is the bootstrap capacitor. So it's acting like a battery. So looking at our circuit, we have our bootstrap capacitor. So imagine this as like a battery that's supplying 10 volts of just 10 volts to our high side rail, meaning that the output is going to either be toggling to 0 volts, so this is going to be 10 volts at the top, or 0 volts at the bottom. So that's kind of the whole purpose of the bootstrap capacitor, is to supply the 10 volts to this MOSFET in order to get it to conduct. Now the sort of genius here is what we're doing is, look here, so we know that the 10, quote unquote 10 volts, the charging of our capacitor comes from VN. And the way it gets charged is we have a bootstrap regulator. So what is going on is we have VN going into a bootstrap regulator, charging our capacitor, and then at some point the bootstrap regulator is just going to shut off the charging of the capacitor so it doesn't overcharge it to like 24 volts or whatever VN is. And then the bootstrap capacitor's job is just to supply charge to the high side driver. So it's a pretty brilliant solution, if you ask me. I thought it was super duper cool. And like I said, this is a super efficient chip. So that means since MOSFETs are, again, voltage driven, there's not going to be a whole lot of charge or a lot of current coming from our bootstrap capacitor high rail. So yeah, that's kind of what's going on here. That's kind of why you need the bootstrap capacitor. So yeah, hopefully that makes sense. If it didn't make sense, then I'll definitely answer your question. Just drop a comment below. So yeah, we'll move on. So it says, see how VN is connected to the drain pin of the MOSFET. So like I said, yeah, that's kind of what I mentioned. So we have VN goes down here, and it's going to our drain pin of our MOSFET, which makes sense if we look at the buck converter basics video. The same thing, VN is connected to the drain pin of our MOSFET. So this actually does look like our traditional buck converter. Now if you have the context of looking under the hood, this looks exactly like the drain pin of our MOSFET. So here we have our MOSFET, and remember the inductor is like sitting right here. So the MOSFET's in series with our inductor, and then it looks just like a normal circuit, if you ask me. Like, to remember, so now that we know the MOSFET is sitting like literally right here in series with the inductor, then everything is pretty normal. Then hopefully all the pieces are coming together with what's going on now. So yeah, that's pretty much what's going on right there. Let's see what else we have. So let's say the source pin connects to our inductor, kind of like what we mentioned, like going again to the converter basics. The source pin connects to our inductor. So that means like current flows through the MOSFET through the inductor, and so that's exactly what's going on. If you look under this chip, we go through the MOSFET and then out through our inductor. And then VN charges our bootstrap capacitor, and then the logic of PWM latch decide when to discharge the bootstrap through the high side driver. So that's kind of what I was talking about with the bootstrap capacitor is what controls our MOSFET thing. So hopefully that makes sense. So yeah, those are like the main things that I want to point out in the circuit, or on looking under the hood for like what's going on in this chip. Like there's some other stuff we can look at, but these are not that important understanding what's going on. The reason I wanted to show this part is because it gives us the full context of like, now hopefully all the pieces fit together with knowing how what our typical buck converter circuit looks like. So yeah, so hopefully that made sense to you. That's pretty much all I want to talk about in this video, and that kind of concludes our deep dive into our LMR chip section of the project. So yeah, hopefully if you made it to this video, or made it to the end of the video, thank you so much, and hopefully I will see you in the next one. Okay, so now we're going to be going through and doing all the component calculations for our circuit. So I'll show you how I picked all the component values for each of these individual components, and I will also be giving any other relevant information for like some relevant parameters associated with each component. Before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton, and be sure to subscribe if you want to stay up to date with any of the future videos in this project. So the first one we're going to start out with is our output inductor. So if you look at the data sheet, you can read this little paragraph here, and it just tells you that the critical parameters for the selection of the output inductor are going to be, of course, your inductance, your peak current, and then DC resistance. And then it gives you some equations down here. So we'll just click over to my notes section, and I'll kind of break down these equations for us. So the first one we're going to take a look at is going to be the minimum output inductance, or LO min, for our inductor. So this is how we actually calculate our inductance value. So it gives us this equation. We have Vn max minus V out over I out times K sub inductor, is what we're going to call that term, times all of this times V out divided by Vn max times FSW, which is our switching frequency. So this is just to reiterate what these variables mean. So Vn max, of course, is our maximum input voltage. V out is our specified output voltage. I out is our output current, and then K subinductor. If we look at the data sheet, it says it's like a ripple current for inductor. So it says KIND is ripple current percentage. So it's a percentage value. So meaning, and they say just a reasonable value to set is 30%. So we're going to go with that as well. And then Vn max, of course, like I said, maximum input voltage, and then FSW is our switching frequency, and that is equal to 700 kilohertz. So if you looked at the earlier video in the project details section, you will notice that we specified Vn max to be 26 volts. Remember, our assumed or our specified V external voltage is equal to 24 volts here. And then I went on and said that any power supply that is specified to be 24 volts, you can bet that it's a very, very small chance that it'll ever exceed 26 volts and or go below 22 volts. So 22 to 26 volts is our happy little window right there that we want to design our power supply for, just for some headroom there. So we put V in max equal 26 volts, V out is 5 volts, which is also something we specified. I out is 1 amp. Again, we specified this in our project details section. K, I, and D, we just read about this in the data sheet, and we know that's equal to 0.3. And then we know also by the data sheet, if we remember the description section of our data sheet, so the switching frequency is 700 kilohertz or 0.7 megahertz. So when you plug all of those values into our equation, it comes out to be 19.23 microhenries. And then what you typically do is, so if you look on part manufacturer and distributor websites, they're not going to have a 19.23 microhenry inductor. What you usually do is you go to the nearest, like what they would say normal value or nominal value. So meaning 22 microhenries is probably like the closest value you'll find when you're looking on manufacturer websites. So we're going to go with 22 microhenries for our inductor, primary inductance. And also, I guess to note, since this says minimum inductance, we want to pick the closest one above this. And we don't want to go with something like, say they had a 19 microhenry inductor. We don't want to pick that because it's below our minimum inductance. So that's kind of the important part for that. So we're going with 22 microhenries for our inductor value. So the next thing the data sheet talks about is we have to calculate, we need to make sure that our inductor is appropriately current rated or rated for our output current rating. And so in order to do that, if you look at this equation, it has ripple current in its equation. So we first have to calculate ripple current. And then we have to plug that into this equation. And also gives us like a peak current as well, just for some more context for the current rating of our inductor. So ripple current is this equation right here. We have V out times quantity V in max minus V out, all divided by V in max times LO times FSW. These variables should be all familiar to us because we just talked about what they all equal. And then we have LO is equal to 22 microhenries in this equation below here. So we get a ripple current value of 0.262 amps whenever we plug those values into this equation. And then we plug in, this is the inductor current RMS value rating. So we plug this value in here, so we get IO squared, which is 1. We specify that already, plus 1 over 12 times this value squared. So we get a value that's just like 1.002 amps for our RMS value. And then the peak current value is going to be, you plug it in, and then you get 1.131 amps as your peak current value. So what I would kind of do is, again, the name of the game is headroom. So we have an inductor value of 22 microhenries. We have a maximum current rating. I would search for something in the 1.6 amp range. And then just keep your DC resistance as low as possible. And that's within reason. Like, I wouldn't fret too much about this. I think the one we have is like in the milli ohm range, if I even have it on there. I don't think I have it on this parameter. But yeah, that's kind of what I would go with. Something like this should work just fine. 1.6 amps gives us plenty of headroom on top of that, so we should be okay there. So yeah, that's pretty much everything I wanted to cover for the output inductor selection. Thank you so much if you made it to the end of this video. Hopefully I will see you in the next one. Welcome back, everyone. So we're going to be continuing on with the component calculation phase of this project. So this is kind of the phase where I go through each and every single component and I show you how I went about calculating the component values, stuff like resistance and capacitance and inductance and stuff like that. And then I also give some insight into other important parameters you need to consider whenever you are selecting the components for your circuit. But before we go any further, please go ahead and drop a like on this video for me. It helps my channel out a ton. And be sure to subscribe if you want to stay up to date with any future videos I release for this project. And so with that out of the way, let's just jump right into it. So next up on our list of components to be calculating is going to be the output capacitor, which is the one we'll be doing our calculations for is this one. If you remember in the circuit design notes section of this project, I talked about the reason I put these two capacitors here, and this is just for higher frequency filtering. And what I meant was like these capacitors are better at filtering higher frequencies than this one, and specifically like this one is the 0.01 microfarad is one is really good at filtering very high frequencies, like maybe like in the megahertz or hundreds of kilohertz range, while this one might be better at filtering frequencies in like the hundreds of kilohertz or tens of kilohertz or something like that, right? So that's kind of where those two came from, and this is something you just kind of pick up as you see more and more designs come out. It's just sort of become second nature. Just slap on a 0.1 microfarad and a 0.01 microfarad cap at the end of your power lines right here, just to smooth them out a little bit more. But the main one that we want to do for the main smoothing line, because if you know this, the current waveform here looks more triangular, and so we do need to pick that up and smooth it out a lot, and that's where this capacitor comes out right here. So just looking at my component notes, if you look at the data sheet, actually what they'll do, so this paragraph kind of talks about, it says the output capacitance needs to be selected based on the most stringent of these three criteria. So what it does is it lays out three different criteria for, and you can go ahead and read this paragraph yourself if you want. I'll just give like a brief synopsis and a breakdown of what we're going to do. But basically what we do is we use these three individual equations, so equations 5, 6, and 7, and we basically pick the highest of these three values here, because it says pick the most stringent of the three values. So we just got to pick whatever equation gives us the highest value. That's the one we have to end up picking for our output capacitance. And it kind of gives you some background into where these three equations kind of come from. So one's kind of like ripple current, and the other is like overshoot, right? If you look at output voltage overshoot, stuff like that. So you can read it if you're more interested in that stuff. But the thing I want to focus on is just breaking down these equations for us. So heading back over to my notes section, like I said, output capacitor selection, three major factors driving this decision. Actually, I break down the three major factors here. So we have one is our load step response, and I'll explain what that is. We have overshoot response, and then we have output voltage ripple. So output voltage ripple should be the most familiar one, just literally just how smooth our output wave is. But then load step and overshoot, we'll talk about those a little more in detail. So number one is going to be our load step response equation. So it's kind of the equation that takes into account what this equation, the capacitor is chosen based on a desired load step response and meaning. So what load step is when you just kind of go from a very low load current to a very high load current. So in this case, we chose, if you look at the data sheet, they recommend, since our specified output current is 1 amp, we want to go from 0.1 amps all the way to 1 amp. So that's a difference of 0.9 amps. So that's what the delta I out value comes out to be. And this is per specification. So this is we want our power supply to behave this way. We want it to have a certain response whenever we go from a load of 0.1 amps to 1 amp. And that response, I guess you could say, is that we want a certain output voltage drop whenever we have a tolerance range. So what it's kind of saying here is that if we all of a sudden go from a 0.1 amp load to a 1 amp load, we don't want our output voltage dropping more than 3%. So that's kind of where those values are coming from. And so what you do is you multiply 5 volts times 3% or 0.03, and you get 0.15 volts. So what that means is if we go from a load of 0.1 amps to 1 amp, we don't want to see a change in output voltage more than 0.15 volts. So I hope that kind of clears things up and kind of gives you a brief explanation of what we're talking about here. And so the way they go about calculating the values for this particular context is we do 2 times I out divided by switching frequency times delta V out. No, sorry, that was a delta I out. And so we just calculated, or we showed what our delta I out and delta V out values are right here. So when you plug those in, you get 17.14 microfarads is the what you get whenever you plug these into the first equation here. So right now our minimum capacitance looks like it's going to be 17.14 microfarads. So then continuing on, so the next one is overshoot response, and this has to do with the overshoot as a term you use in feedback loop. If you've studied feedback systems and stuff like that, so it's just kind of the response whenever we're trying to maintain a steady state output voltage, and our output capacitor has an effect on that, on its ability to do that. And so kind of what we're looking at here, so obviously we have our output inductance times I sub OH minus I sub OL. So OH is the current output under heavy load, and then OL is current output under light load. And then VF is final peak output voltage, and then VI is the initial output capacitor voltage. So we have it's kind of the same story with the load step actually. So we're considering heavy load to be a 1 amp load. Per the specification of our power supply is only supposed to be able to supply 1 amp, so that's a heavy load for this power supply. And then a light load is 0.1 amps, which is just like 10% of our maximum output load, basically. So OH is going to be 1, and then OL is going to be 0.1. Remember, you square these terms. So VF is the final peak output voltage. So this is per our specification. We have 1.03 times 5 volts. So the final peak output voltage is 5.15 volts. So this comes from our maximum ripple voltage specification. This is also where this 3% value came from earlier on, is that we're trying to keep a maximum ripple voltage of like 3%, or a peak output voltage of no more than 3% above our nominal output voltage. Okay, so we have that value as 5.15 volts. So then when you plug all this in, so you get 1 amp squared minus 0.1 amp squared divided by 5.15 volts squared minus 5 volts squared, all that times 22 microhenries, you get 4.13 microfarads. So this value is still lower than this one, so we're still sitting at, looks like we still need at least 17.14 microfarads of capacitance here. And then moving on to our final equation, we have C out, and this is for the output voltage ripple, just under steady state. So we have V out ripple divided by IL ripple. So we already calculated our IL ripple to be 0.262 amps, and then we want a 1% voltage ripple per specification. So that's just under like normal operating conditions, not under like any like heavy load step conditions or overshoot conditions or anything like that. Just normal operation. We want a voltage ripple of 1%, or 0.05 volts. And so when you plug those values in, of course FSW is switching frequency, you get 1 divided by 8 times 700 kilohertz times 1 divided by this quantity right here, which is 0.05 volts, times 0.262 amps. So that's kind of where those two values came from right there. And then you get an output capacitance of 0.93 microfarads. So whenever you look at all of these values here, like I said, we picked the most stringent value, so the winner looks to be 17.14 microfarads. So that's like our minimum output capacitance. And then the answer is we kind of go with the closest nominal value, again, that you can find on the manufacturer part website. And I don't know, like I think I ended up picking something at 22 microfarads. So I honestly don't know if that's the closest, but it's a close value, and it's not going to hurt to have a little more capacitance. So it's somewhere it's in the neighborhood, and it's a close nominal value is kind of what we'll say about that. And then finally, if you look at the data sheet, they talk about making sure to have a low ESR, so maximum output capacitor have to meet the output voltage ripple specification. So also what they kind of mention is the output like ripple current capability. And so what that kind of means is, how would I explain this? So we kind of, if you watch this channel, if you watch some of the videos, I'll mention how like in the real world components aren't perfect, and they have a lot of what you call like parasitic elements to them. So in a capacitor's case, they have like what you would call like an equivalent series resistance, or maybe like a parasitic resistance, where it's really like a resistor in series with a capacitor. or you could replace the capacitor like that. It basically has like a resistor value in it, and that's where this RESR value comes from. And is it anything you know about resistors? They dissipate heat when you have current passing through them, and so what will happen is if your RESR value is too high and you have a really high current going through it, you can end up dissipating too much heat for your capacitor, and it'll just heat up and it'll cause it to blow up, basically. So that's why we kind of want to keep our RESR value as low as possible, just to minimize the amount of heat dissipated through that. And it actually gives us the equation for that. So RESR has to be less than 0.05 volts divided by 0.262 amps. So that means just keep RESR less than 190 milliohms. And that seems, I think that's pretty easy based on, if you look at the manufacturer's website. I don't know what ours is. I don't know if I put it on the data sheet, but it shouldn't be too hard. You can find stuff in the tens or ones of milliamps. So it's not too difficult to find something this low. So that's pretty much everything I wanted to cover for the output capacitor selection. Thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Welcome back, everyone. So we're going to be continuing on with the component calculation phase of our project. So this is kind of the phase where I go through each and every single component on this circuit and kind of explain all of the calculations behind how I chose their component values, and then I also give any relevant information into other important parameters that you might want to consider for selecting a component for the circuit. But before we go any further, please go ahead and drop a like on this video for me and hit the subscribe button if you want to stay up to date with any future videos. So with that out of the way, let's just jump right into it. So now we're going to focus on our output diode. So if you just go ahead and let's take a look at our buck converter basic schematic again. And so the output diode, remember, its job is to basically just connect this back pin of our inductor to ground for whenever the switch is open. So that means whenever the inductor current is, when the inductor is supplying the current, then the diode is what enables the circuit to be closed in a one-directional manner. So looking at the data sheet, if you see the diode selection paragraph here that they talk about, there's some main considerations that are our voltage, our peak reverse voltage, and then our current our current capacity or our current rating of our diode. So it's pretty simple actually if you just look at the component calculations. So here we just say the breakdown voltage should be 25% higher than the maximum input voltage of our power supply, right? And so in this case, the maximum input voltage is 26 volts. And so if you just multiply that times 1.25, you get 32.5 volts. So this is going to be like the exact value, and just make sure you pick a peak reverse voltage that's a little bit higher than this, I would say, or the closest nominal value I would say. So with this one, the peak reverse voltage is 40 volts. So that was just a close nominal value. And I've also talked about this before, and one thing you'll get a feel for is like what an quote unquote like extreme value is for a component parameter, meaning let's just take this diode for example. So you have peak reverse, max voltage, and then you have current rating. So what I'm kind of contending here is that since the current rating is the extreme value in this case, meaning that finding a diode with a 1 amp current rating is going to be the harder thing to do. And maybe if I can phrase it differently. So if you were to put in your input criteria for finding a component and you selected 1 amp as a current rating, you're going to easily find something with a 32.5 volt peak reverse max voltage. Okay, so this one I'm saying, whenever you start your search, I would say start with a 1 amp current rating as one of your filter constraints, and then try to find something with a high peak reverse max, and not the other way around, because you might find dozens of diodes with peak reverse max voltages of around 32 or 40 volts that don't quite have the current rating that we need. So that's kind of what I'm talking about there. And that kind of just brings us to our next thing, of course, is going to be our peak current rating should be greater than the maximum current. And so that means our peak current rating needs to be actually greater than 1 amp. So that's even a little bit more extreme value in the context of our 32.5 volt peak reverse max voltage. So I think I chose something right around 1 amp because I think the data sheet even said a 1 amp to 2 amp diode is a good starting point. So I don't know what so this one's 2 amps actually. So that's kind of what I chose for our diode current rating right there. And then another thing you can consider a little bit, and this just affects efficiency, is going to be the forward voltage of our diode. So this was like a Schottky diode, and that's one thing you'll kind of notice in like modern circuit design is that Schottky diodes are starting to take the place of your standard diodes a lot more, because Schottky diodes, if I remember correctly, typically have a lower forward voltage. So like 0.05 volts. Think of something like an LED, which usually has a forward voltage of like 2.2 volts or something really high. That's just burning up power. So what a 0.55 volt forward voltage with our diode does is allows us to be a lot more efficient. So that's kind of one thing you might consider as well if you're considering, like, if efficiency is a big requirement for your project, then try to find something with a lower forward voltage. And so 0.55 is a pretty good value, I would say. That's pretty low. Like, you might get some lower stuff, but you'll probably have a hard time finding something that meets the other parameter requirements. So that's pretty much everything I wanted to cover for the Schottky diode selection, or our output diode selection portion of this project. Thank you so much if you made it to the end of the video, and hopefully I will see you in the next one. Well, welcome back everyone. This is the component calculations phase of this project. So this is where I go through each and every component and show you all of the equations and the calculations I did in order to determine the component values. And then I will also go through some of the relevant parameters to selecting components, and give you any like notes or thoughts I have on that. But before we go any further, please go ahead and drop a like on the video. That helps my channel out a ton, and I'd really appreciate that. And be sure to subscribe if you want to stay up to date with any future videos in this project. So with that out of the way, let's just jump right into it. So next up on our list of components to do the calculations for is going to be our input capacitor. So let's just go take a look at my component notes. So there's several equations and notes I have here for determining our value. Let's just take a look real quick at what the datasheet says. So actually only two small equations, but if you look at the notes for this paragraph, if you read it, it actually gives you some more instructions on something like the materials we need to use, and as well as some of the other important parameters such as the ESR value. So I think I have that in my notes actually. So what the datasheet suggests is that we find something that is low ESR and made of some type of ceramic material. And so that's kind of what this actually means. X5R and X7R denotes the type of material that is used in the capacitor. I think it's what is used for the capacitive plates, the actual plates of the capacitor, and not like some type of insulative body or something. I think. I'm not 100% sure on that though. So yeah, whenever you're searching for a capacitor for your input capacitor, just search up something. I went with X7R because I'm more familiar with those types of ceramic capacitors. But yes, make sure to just filter out stuff and make sure it's either X5R material or X7R material. And then we obviously want something that's extremely low in ESR value. And I actually mentioned this before in the output capacitor selection section. And the reason you want something with low ESR is because there is if the capacitor is charging and discharging, i.e. If there is current flowing onto or out of the plates, and you have an equivalent series resistance present, you're going to be generating some heat through power dissipation, right? Because you have a current flowing through a resistor basically at this point. And so there's going to be some heat loss. So your capacitor is going to heat up. And so with too high of an ESR, you're going to be generating more and more heat, and that could go over, you can end up damaging your capacitor that way. So that's kind of why they're talking about getting a low ESR value right there. So that's kind of the main reason for that. Interestingly enough, I think the main equations that they talk about aren't even related to capacitance. It just straight up tells you, yeah, pick a value between 1 microfarad and 10 microfarads. So I think what I end up doing, there's some other equations that I use to determine that value, but I think what I ended up going was 4.7 microfarads. Originally I had considered something that was 10 microfarads, but then whenever I went and searched for parts, I found out that these values that we calculated for are better suited. Like I found something that was more suited that ended up being 4.7 microfarads, and it fits within the window of 1 to 10. So I went with it. So yeah, let's just go ahead and see what the datasheet tells us about. Let's see what it says. So it looks like it's like this. We have the current, the IRMS current of our capacitor. So it's like this is like the input capacitance current, right? So we have the equation for that. So the rating, or this is like the ripple current, basically. The ripple current rating must be greater than the input ripple current that we experience. And so the input ripple current we experience, I believe, is this equation right here. And so it is just equal to I out times the square root of V out over V in min times V in min minus V out over V in min. So we kind of established what all these values are earlier on in the project videos. So hopefully you already know what they are. So it's 5 volts divided by 22 volts times 22 volts minus 5 volts over 22 volts. So whenever you plug those in and then crunch the numbers, you get an RMS, a ripple current of 4.419 amps. And so kind of going back to the ESR value, this is the amount of current that we should see flowing onto and out of the plates. That's kind of why they're talking about ripple, because it's going in and out and in and out. So it's like oscillating. And so it looks like we have 0.419 amps of ripple current, and then multiply that by time, or square that, and then multiply it by our RESR, and that's how much heat our capacitor is generating. And then if you look on the data sheet of the capacitor, it'll tell you per like how much heat is generated per the amount of ripple current that is experiencing, right? So that's kind of where those values are kind of converging on and helping us determine if our capacitor is appropriate for us, so appropriate for this application. So hopefully that makes sense to you. If it doesn't, then drop a comment down below and I can try to give a further explanation for it. But just take some digging through the data sheet and just a little bit of reading, and you kind of get a good understanding of what of whether your capacitor is appropriate or not. The next thing we want to consider is going to be our ripple voltage. So we have an input ripple voltage that we don't want to, or we just want to know our input ripple voltage actually. And so let me see, like the reason for that is for this design, let's see. Okay, so the next thing we're going to take a look at is going to be the input ripple voltage, just so we have an idea of what to expect for this value. So it just tells you delta Vn is equal to I out max times 0.25 divided by Cn times FSW. So if you take a look at this, we already know some of these values. So we have I out max is going to be 1 amp times 0.25. And for this, I ended up putting in 10 microfarads for this calculation, but really it could be 4.7. Since we have that window of stuff to pick, I just picked 10 because that was my original decision. But then 4.7 would work also, and then that would just give you a slightly higher ripple voltage there. So it's not too big of a deal, though. It just tells you, like if you look at the data sheet here, it talks about the input ripple voltage is 162 millivolts, and all this value kind of does is it just tells us how much like with the higher your ripple voltage goes, that means just it's the more difficult it becomes for your like controller, your converter chip, to maintain a steady state output voltage, because it's just constantly having to do recalculate in order to change the amount of current going through that input, going through that inductor. So but yeah, at the end, as long as you pick a value between 1 microfarad and 10 microfarads, then you're going to be okay. The next thing I would talk about for picking this input capacitor is make sure that it's appropriately rated for the voltage. Since we have a maximum input voltage of 26 volts, make sure your capacitor is rated greater than 26 volts. You can find something maybe 30 volts or even up to 50 volts. Usually the way I do it is, as long as I don't have to go up a package size, I just find the highest voltage rating I can. So For example, like you can find a 50 volt, like if you're looking at a capacitor, two capacitors that have the same capacitance and the same other parameters, they're both like 0603s, but one is rated at 25 volts and the other is rated at 50 volts. Just go with a 50 volt one because you don't really lose anything for the extra voltage rating. And so it ends up just working out for you that way. So that's kind of how I go about picking my capacitor voltage rating and my capacitors and stuff. So that's pretty much everything I wanted to cover for this portion of for the selection of the input capacitor. Drop a comment if you have any questions. So drop a comment down below, and I'll be happy to answer it. So yeah, that's pretty much everything I want to say. So thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Okay, so we are in the component calculation portion of this project. So this is where I go through the entire circuit and I show you all of the equations and calculations I did in order to figure out the component values. And then I also give some relevant information to some of the parameters I think are important when it comes to selecting your components. Before we go any further though, please go ahead and drop a like on the video for me. It helps my channel out a ton, so I'd really appreciate that. And go ahead and hit the subscribe button if you'd like to stay up to date with any future videos in this project series. And with that out of the way, let's just jump right into it. So we are now on to the bootstrap capacitor calculation section, or they call it C boot. But remember, this is if you remember earlier in the project series, I explained the functionality of this capacitor is to actually supply the necessary voltage in order to drive the gate pin of the MOSFET in order to allow it to conduct. So if you read the data sheet, it just basically tells you, let's just check my notes here. It just says 0.1 microfarad capacitor or larger is recommended, and so it looks like we went with a 0.47 microfarad capacitor. And remember, like the capacitance of the capacitor in this case is just going to determine like how much charge it can store on the plates, and so it's basically how much like current or how much charge, and it's basically a metric of how long it can hold that gate open for us before it gets discharged. And since we know MOSFETs are voltage driven, they consume very little current. It's really not necessary. That's why you can get away with such a tiny capacitor, right? They also make a note. They say if VN is close to Vout, a larger capacitor is recommended, but it says the range is 0.1 to 1. So I think we're okay there. We have 0.47, which is right in the middle. It recommends to use an X7R, X5R dielectric, and if you remember earlier on in the video series I explained this is just a type of ceramic capacitor, and this refers to, I think it's the material that the actual plates are made of, but I'm not 100% sure. We just know this is just a type of ceramic capacitor, and I believe I went with X7R just because I'm more familiar with that kind. And I think the differences could be, usually the differences could be how easy it is to achieve a certain capacitance value given a certain package size, maybe some thermal characteristics. So it's really not that big of a deal in this application, so I think either or is fine, so whichever you'd like, but I think I went with X7R. And then it says make sure the voltage rating is greater than 10 volts. Now, maybe you already figured out the reason for this, and that's because the voltage value of this capacitor is usually going to be around 10 volts, right? Because remember, if you're familiar with, if you ever design circuits with MOSFETs, a lot of times their gate voltage, the required voltage in order to drive, to allow the MOSFET to fully conduct, is around 10 volts. So that's why they say get a capacitor with a voltage rating greater than 10 volts, because you'll probably be driving that MOSFET by more than 10 volts, so you'll be charging your capacitor up to a value of around 10 volts. So that's kind of why they say that there. So make sure that's an important note. That's pretty much, I guess, everything I wanted to cover with this capacitor here. I don't think there is too much other information that's relevant. Okay, another general tip I usually have is I like to start out with the 0603 package size as a starting point, especially when going into layout. And the reason for that is because of routing requirements. That's about as small of a package as you can get and still be able to route between the pads, and that's like a little pro league strat I like to use when doing the layout portion of the project, and so just is a creative way to use less vias and have a little more efficient routing patterns. So 0603 is about as small as you want to get, and then bigger, of course, it's easier, but then you can't place your components as tightly together, and so it would affect your board size by a little bit. But it's still, if we're going for the smallest board, then I think 0603 is sort of that happy medium where it's about as small as you can get while still being able to route through the pads or between the pads, and then it's like I said, it's as small as you can get. I don't know if there's anything else I wanted to say about that. So yeah, I think that's pretty much where we can wrap this one up. This will be a short one. Just drop your questions in the comment section below. If you have any, then I'll be happy to answer them. And thank you if you made it to the end of this video, and hopefully I will see you in the next one. Welcome back, everyone. We are in the component calculation portion of our buck converter project. So this is the part of the project where I go through every single component and I show all of the equations I use to do the component calculation. So it's how I derived all of the values. So like your capacitance values, your resistance values, your inductance values. And then I'll also go through and list out any important details that I think are relevant when it comes to actually selecting a component, maybe something like the capacitor material type or the inductor current rating, package size, stuff like that. So I always go through all that stuff as well. Before we go any further though, please go ahead and drop a like on the video for me. It helps my channel out a ton. And if feel free to subscribe if you want to stay up to date with all the rest of the videos in this project series. And with that out of the way, let's just jump right into it. So we are now on to the feedback portion of the project, meaning we're going to be calculating, I'm going to show you how I calculate the values for these two feedback resistors. And if you remember early on in the project, the job of these feedback resistors is to set a particular voltage here that feeds into our feedback pin and allows our buck converter chip to monitor the output voltage and then modify its duty cycle or what have you. I think it pretty much, this one's a fixed frequency, so it should only modify its duty cycle. But just in order to meet our specified output voltage is basically what we're trying to do here. So let's just go into my notes and I can just kind of run through what I did here. So look in the feedback resistors. So it says the output voltage is set using the feedback pin and a resistor divider connected to the output. So that kind of was also, if you need more information on this, I went in, just check the earlier videos. I went over this in great detail, kind of what goes on the inside of the chip. So that could be very helpful to you. And then the data sheet, if you look through it, it gives you this equation where V out is equal to 0.765 times the quantity 1 plus R1 over R2. So here we have two variables, so we have to assume a value. And in this here, I say make R2 equal to 10K. And the way I got that value, if you look at the data sheet, they say typically R2 will be given as 1K to 10K for a starting value. So I just picked 10K as a nice round number. Other places on the data sheet, they use 10K as a value. So I just figured make it easier on us and let's just go with 10K for that resistor. So R2, this, not to be confused, I'm sorry, this designator says R2, but really it's talking about this bottom resistor here is 10K. So sorry if that's confusing. So this is supposed to be correct. So the bottom resistor is supposed to be 10K, just like this one is denoted. And you can even see it later on in like the data sheet right here. So something like this is what they're talking about. And so then when you plug it into the equation, you get this, this is what it looks like. And then you have R1 equals 55.35 kilo ohms. And so what you then do is kind of like in the case with when we did the inductor calculation, is you just go to the nearest nominal value that you can find on the manufacturer's website, whoever you're looking for to produce, you're looking for whatever website you're looking on your resistors, you're looking for your resistors on, like Vishay or someone like that. Well, I think when I checked, they have like a 54.9K ohm resistor. And I think the specific one I ended up finding was 55K exactly. So that's what I ended up choosing for my resistor value. And then I end up choosing a 1% tolerance. So I think tolerance is a good thing to talk about here as well. So if you don't know what tolerance is, it's basically how much deviation from the nominal value that this component could possibly be. So just imagine whenever they're making these resistors at the factory, so you got hundreds of thousands of 55 kilo ohm or 54.9 kilo ohm resistors coming off the line, and they're being tested in an automated manner, right? And so there is a constraint tolerance, right? Because they're not going to be 55K on the dot. That may be 55.1K, 55.01K or something like that. So they could have, plus or minus a few ohms on each side. And so what the tolerance does is it allows, what the tolerance tells us is how much on each side is allowable for our product spec. Meaning, like, let's say we need a really, really precise voltage on the output. So we could specify a tolerance of like 0.01 or 0.1%, right? So it's only 55K ohms plus or minus 0.1%. So I don't know what that is, like 50 ohms or something. In order to keep and say our circuit would get absolutely ruined if that wasn't, if it wasn't that close. All right, so then you would pick a resistor value with a really precise tolerance. In some cases, it doesn't really matter that much. Like when we get to the calculating the resistors on the input side, you'll see that you can actually probably have a much looser tolerance for your resistor values. You can probably have something like 5% or something, because this is, in our case, this one isn't that important. So that's just good information to know. You'll see a lot of common values are like 1%, 0.1%, 5% value. So just understand kind of that's what that means. And so 1% tolerance, because we just want to have a nice tight constraint for our output, nice, very tight window for our voltage as well. And then of course, important things when it comes to resistors are make sure that it's the power rating is appropriate, meaning however much power needs to be dissipated by our resistors. Make sure it's appropriate. I think for mine, I don't think we have to worry at all, because at 55K, 5 volts divided by, or it's like the amount of power that resistor is. So you have like 25 divided by 55,000. I don't even know how many. That's like in the very, very tiny amount of milliwatts, right? And so we're good. We're like at 1/10 of a watt here. So we're like at 100 milliwatts, and we're way below the 100 milliwatt threshold for this resistor. And then it's the same here. So that's another thing. And then of course I also mentioned like package size is a good thing to consider as well. Make sure I select like 0603 is a good starting point, and I kind of talked about this in the other video, because that's the minimum package size that you can kind of comfortably route through, and being able to route in between pads can really make your layout much more efficient, and you can avoid using vias, and it looks pretty cool to me. It's like a neat little trick I like to do. So that's kind of a tip I'd have for that. But that's pretty much, I guess, everything I wanted to say covering the feedback resistor calculations. Go ahead and drop a comment down below if you have any questions, or if you have any project ideas you want to see on this channel, then definitely I'll leave a comment down below. I'm always open to project ideas. I love teaching people how to design circuits, so let me know. So thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Welcome back, everyone. We are in the component calculations portion of our buck converter project. This is the portion of the project where I go through each and every component, and I show how I went about calculating the component values for these components. And then I also give some information I think is relevant when it comes to selecting your components. So I might talk about like package size or tolerance or certain materials that you might want to consider. Stuff like that. Before we go any further though, please go ahead and smash the like button for me. It helps my channel out a ton, so I'd really appreciate that. And if subscribe if you want to stay up to date with any future videos in this project series. And with that out of the way, let's just jump right into it. So we are on the input feedback resistors section of this component calculations portion of the project. So this is, if you didn't watch the other video, I actually give a detailed breakdown of what all these pins do and kind of the inner workings of the chip. And so just a brief summary of what the shutdown pin does is this just sets the voltage, the quote unquote under voltage lockout. value. So basically, if the voltage of the input, if the input voltage drops below a certain value, then the chip will just stop working altogether. And there's a number of reasons you might want to do this in like a real world scenario. We're not gonna really get into any of those. I just think it's useful to understand how this works and how you go about setting this value. So that's kind of what we're gonna do today. So let's just go ahead and take a look at my notes I have here for the shutdown resistors. So if you look at the data sheet, it says the LMR 14010A chip enters shutdown if the shutdown pin falls below 1.25 volts. Okay, so that means basically what ends up happening is, so say you have like 24 volts on this input, it gets voltage divided down into a value, and then as say your input voltage starts to fall, this value starts falling. So you want to make it such that whatever your cutoff threshold is, like say your cutoff threshold was 12 volts. So that means whenever this value is 12 volts, this value should be about 1.25 volts. So that means if VN dropped below 12 volts, this value would drop below 1.25 volts, and then the whole chip would just shut down. So that's kind of what the idea is here with understanding how this thing works. So here's the equation I use for figuring out what resistor values we should use, and I'll explain all the variables we have. So this is actually just a slightly modified version of your typical voltage divider equation, and actually if you look, I used a voltage divider equation. So all I did was, just for the sake of clarity, I just changed V out and VS to V shutdown and V in, because if you look on the diagram, that's what it would be. So V out, which is this value, so the value right here between our resistors, which is this value right here, is going to be our V shutdown value, and then VS is going to be V in. It's going to be our input voltage value. So in our circuit's case, like say we have a nominal voltage of 24 at the top, and then it's getting voltage divided down into whatever at the bottom. And so what we end up doing is we pick the voltage at the VN, quote unquote, the VN voltage, or the VN term in this equation is not going to be our nominal voltage. We actually want it to be the threshold voltage, meaning as if VN drops below a certain value, that's when we want to shut off. We don't want it to be, in this case, the actual VN that we specified. We don't want it to be 24 volts. We want it to be a different value. And so for this case, I just chose 12 volts, meaning if VN becomes 12 volts or less, the chip is going to shut down. That's what this equation is kind of telling us here. So we already know V shutdown is equal to 1.25 volts. So kind of what we're trying to do is, whenever VN is equal to 12 volts, we're trying to make V shutdown equal to 1.25 volts, and we're using a voltage divider to do that. So I hope that it makes sense there. If it doesn't, drop a comment down below and I'll be happy to answer any questions. So I went ahead and plugged the values in here. And quickly, I should also note that I just arbitrarily chose 10K as the value for R2. Just kind of, we did the same thing for the other side, so I just figured, just for simplicity's sake, just do it again on this side. I mean, it worked once over there. It's fine with working over here, right? And so what we end up doing, if you do the math, then it comes out to about 86 kilo ohms is what you want R1 to be. And then I just found this should be kilo ohms, not ohms. Sorry if that's confusing. This should be a kilo ohm. So if you look on our schematic, we have 86.6 kilo ohms for our resistor value there. But that's what the math comes out to be, is you have 86 kilo ohms and 10 kilo ohms for our two resistor values, and that's what's going to cause. So again, just to be clear, what's going to happen, like say this value drops to 12 volts, that's when this value will be 1.25 volts. So if VN drops below 12 volts, the shutdown pin will drop below 1.25 volts and then initiate an under voltage lockout scenario. So that's what's going on here. That's what the math tells us, and that's what we've specified. So I hope that's clear to what's going on here. If it's not clear, then like I said, drop a question in the comment section and I'll be happy to answer it. The only other comments I want to make on this is, I mentioned in the other feedback resistor calculation portion, is that resistor tolerance is a factor in these sometimes. And for this one, since at least in the context of our project, we don't really have a very tight window. Like it could shut down at 11 volts. It could shut down at 13 volts. We don't really care, at least for this project, right? We haven't specified that we need a very tight, window on that under voltage lockout scenario. So you could pick a 5% tolerance resistor or whatever. Usually, one thing I don't know if I mentioned in the other videos, the tighter the tolerance, usually it's a little bit more expensive for the resistor, right? If you have like a 0.1% resistor, it's probably gonna be a little bit more expensive than a 1% resistor. That's just because the nature of, say, when you're manufacturing them, you're gonna have more you're gonna have a lower yield the tighter your tolerance is. So hopefully that part makes sense. Is that if you have a really tight tolerance, you have more failures coming off the line, and so you're just gonna have a lower yield, and you have to make up for the lack of the lower yield, right? So that's what causes those to usually be more expensive. So that's why it could benefit you to pick something with a not as tight of a tolerance, because it could just make it cheaper by a little bit. Like I said, 0603 is probably a good package size to start out with here. Make sure your power ratings are appropriate. Make sure these resistors aren't dissipating more power than they can handle. And the reason we go with a package size of 0603 is that's because that is the value. That's like the minimum package size that I found that you can route your traces between pads when you're doing your PCB layout, and that's just a very nice strategy in order to make a cleaner layout where you don't have to use as much vias. It looks pretty cool to me as well, so I like doing that. So I think 0603 is a good place to start, and if you need to go smaller, then you can always go smaller, but you just know you won't be able to route between the pads then. So that's just one thing to consider there. I think that's pretty much everything I wanted to cover for the input feedback resistors, or I guess I could say the input voltage divider resistors. And so yeah, thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Okay, welcome back everyone to our buck converter project. We're actually now on to the PCB layout portion of the project. So this is where I'm going to go through the actual layout of our board. So if you look at it in 3D, I'm just going to show you how I went about placing the components, doing all the routing, any other board notes that I have. I actually have a note section we'll go over. Stuff like that I think is relevant to doing the layout for this. But before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton. And subscribe if you want to stay up to date with any future videos in this project series. So with that out of the way, let's just jump right into it. So I think I'm going to break this portion of the project down into 3 sections. So section 1, we'll go over just general board notes and just general layout notes. We'll probably talk about some of this stuff, my setup, and we'll go over some of the just board properties we have. We won't talk about like component placement, or we'll talk about component placement and routing later on. So yeah, so let's just jump right into it. So this is just your typical 2-layer board. There's nothing too fancy with anything, any of the stuff I did in terms of, we'll go over the layer stack manager in a second. But yeah, it ended up coming out to be about 4.25 centimeters by 2.98 centimeters. So that is extremely small. If you don't, I don't even know, like this is like 2 inches by like 1.5 inches or something. Like I think a centimeter is what, 2.4 inches or something like that. It's incredible. This is a very small, like this thing will fit in the palm of your hand. I mean, looking at the connectors we have here, like the connectors are pretty massive looking on this tiny little board. Another thing I'll note is, so whenever you're doing layouts like this, take note of what components are really your biggest space wasters, in the sense of what takes up the most space on the PCB. And actually you'll notice, so for one, it's our connectors. This is actually a right angle connector that sticks out a little bit over the edge of the board, I think. If not, it comes right up to the edge. So our connectors are our biggest things on the board, and then the next thing you'll notice is the inductor. So this kind of going back to whenever you're designing your schematic and you're picking your inductor out, keep that in mind, because one of the things you could have thought about was, oh, that equation gives us an inductance, like a minimum required inductance for this. So why don't I just pick a value that's like 2 or 3 times bigger than what I need, because you know it's still going to work and it's just for safety, right? Then we'll have an extra smooth signal that's really powerful, really stable. And the same thing goes for current rating and stuff like that. Why don't we just pick a massive current, something that can handle 5 amps instead of 1? And the reason is size. Whenever you pick a value, like if we were to look at an inductor that has a much higher inductance and current rating, it would just be much larger. And so whenever you're trying to make a board as small as possible, that's why it kind of matters that you pick, a particular value. That's kind of why we want to hug what would be called like the limit, like the edge of our design specifications, because this could end up costing us a lot in like manufacturing costs and just size. It could cost us a lot of real estate on size, because a lot of times whenever you're designing your PCB, you get told how much space you have before you start doing the PCB. So you're trying to squeeze everything in as tight as possible. So it's not just like we're having fun and just trying to see how small we can get it. It's you need 5 square inches and they're giving you 4.9. So that's kind of how it goes. So yeah, pay attention. I would say the inductor took up a lot of space and our connector took up a lot of space. Everything else super tiny, right? You can fit all these things right on top of each other. It's not a big deal at all. The other thing I want to go over, and I have some notes on this, are our mounting holes. So if you look on the project details, I think I specified we wanted with an M2 screw. I ended up going with 4 M2 screws because you'll probably see this is very common with a board this size. I don't really know if you'd need 4 M2 screws, but for future reference, a lot of boards you'll see just get mounted with 4 screws, and these just go right into like a heat sink or some type of mounting bracket that holds the shrouding or the housing for your PCB. Whatever protects it usually is mounted with some mounting screws. So I think it's good to get practice with seeing these 4 circles, these 4 mounting holes just on the corners of our PCB. I ended up making it M2. Let me see, I have some notes on this. So the M2, so I just pulled, this is actually for an M4 screw, because I think I was considering M4, but then I realized how tiny our board was. I'm like, okay, we can go M2 because our board is also super light. So what I just ended up Googling like the actual physical dimensions for the M2 screw. And so it just tells you like, this is for an M4, mind you, but just know this is how I got this value. And so I ended up making, if you look at this, I don't know if it'll tell us how big the circle is or the hole, but I ended up making an M2. This is in metric, so we need to change that. So this is, looks like the hole is like 5 millimeters. Hole size is 2.5 millimeters. So I gave us, since it's the thread, so M2 means the thread is 2 millimeters. And so I gave us 0.5 millimeter of wiggle room on the outside. And then I ended up making the actual, the pad size 5 millimeters. So we have like a 2.5 millimeter annular ring. And then I also got that value from looking at how wide this H value in the head. And again, this is for an M4 and not an M2, but it's the same exact concept. They'll tell you how wide the head is. And so I just made enough room, because a lot of times these screws will be used to ground to chassis, right? You'll have a big metal frame that's grounded for safety, and so you want your board to also be grounded that way, especially if you have like a power supply or something that plugs into the wall that has like an earth ground component to it. A lot of times they'll tie that earth ground to chassis as a safety ground. So that's why it's important to have your annular rings really nice and big and nice and conductive for our mounting screws. If you look, the copper pores I poured connect to our mounting screws. So these 4 mounting screws are in fact, our mounting holes are grounded. And so when the screws into it, it'll ground our heatsink or whatever is, the big frame will be grounded as well. Going into actually real quick before we talk about the layer stack manager. So this is our general, like template that I have set up for, like our PCB layout portion of the project. And so we have just some fabrication notes on this layer, and I'll talk about those for a second. We'll probably start adding those as we do more complicated boards, but this is what you'll send over like this layer. It's important to have like a layer like this because your fabrication house will actually see this whenever you send over like the Gerber files or your fabrication documents. They'll see this layer, and it's just a nifty little notes layer so that they have everything right there collected with all the pick and place files and your BOM and all that stuff is all nice and orderly. You don't actually have to send like a separate sheet. It's like right there with your layout documents, any fabrication notes. And so the only note that I end up throwing on here for right now is no silk screen allowed on copper pads. Remove at manufacturer's discretion. And so the reason we have this note here is because right now, per our layout rules, we have the silk screen to copper pad tolerance. I think it's set at something insanely small. It might even be 0 mils. It's something like 0 mils or 1 mil, because what I'm saying is my PCB layout rules allow me to place these designators as like literally like almost on top of, I could probably place it on top of our actual pads, and that's just because a lot of times it gets kind of annoying, even like this. So yeah, I think like this might even, well, I don't know, this might not be a problem, but a lot of times placing these designators gets to be really like, you know, cumbersome and annoying, you know, especially whenever you do all this work to route the layout, and then these stupid designators are just, you can't put them close enough, especially because they're so big too, because the point of these is so you can, the human eye can read them, so they're not, you can't really shrink these. It doesn't really behoove you to shrink them, so you're kind of just stuck. Let's move this right here. Sorry. So yeah, and I'll put this one right here. So yeah, so that's kind of one thing that's why I have such a tight tolerance, because these things have to be so big that it doesn't really like you're kind of stuck there. So that's why I also put the manufacturer's note to remove ink from the pads, because it could mess with our solder joints, right? If you have ink interfering with the contact of the pad, then, you know, soldering you could have a poor connection there. It could affect the actual performance of your board, so we don't want that. So that's like the only note I have here. Like I said, we'll add to these as we get you know, more and more complicated boards, and as we learn more about layout together. So don't worry about that. Then finally, I guess we'll go over our layer stack manager. I mean, there's nothing too fancy here. Like I said, it's a typical 2-layer board, just a bottom layer and a top layer, and they're both signal layers. And what I ended up doing was and we'll go over this in the routing portion, but I make them signal layers, and then we end up just doing copper pores on these for our ground planes, and then the copper pore would just fill in around the area where there's no ground plane, or where there's no traces, so the ground plane will fill itself in. So it's not too complicated. So we have, oh yeah, also I should say, the reason why we did a top layer and bottom layer is because a 2-layer board during manufacturing is about as expensive as a 1-layer board. Now a 4-layer board, that's unnecessarily expensive. We don't need to do that in this case. But like what I mean is, if you look at I could have done this on 1 layer easily. In fact, like the bottom layer is literally just like a ground plane pretty much. I have a couple vias, but I could have done it with 1 layer, I'm pretty sure. Like I think I have 2 vias, so that I'd have to figure out how to get around. But besides that, I think I could have done it in 1. So you're thinking, well, you know, 1-layer board is so much cheaper than a 2-layer board, so why don't we just go 1 layer, save money? And it's really not much cheaper because of the way the manufacturing process is done. It doesn't really cost a whole lot extra to add an extra layer to make it an even number of layers. But if you had to go from, you know, 2 to 4, then that's an extra amount of cost that you don't want to incur. So yeah, the copper weight we used was 1 ounce, and that is a very typical copper weight that pretty much every PCB manufacturing fab house will have. It's one of the most common ones, so we're not getting, you know, any additional cost added on there. If you started changing it to something crazy like 0.75 ounce copper, or, you know, 1.5 ounce copper, that might be okay. But like ½ ounce and 1 ounce, I think, or 1 ounce and 1.5 ounce, I think, are some of the most common ones you'll get. And everything else is pretty much standard here. Like this board is very simple. It's not too complicated. We don't have an insane amount of we don't have any mechanical considerations for this board right now. So we didn't have to really change up anything for, as far as the layer stack manager goes. So yeah, it's very typical. You have your overlay, your top solder, top layer, then your dielectric in the middle. Then you have your bottom layer, bottom solder, bottom overlay. So nothing too fancy there. So that pretty much covers everything that I wanted to for this first portion. In the next sections, we'll talk about component placement, and then after that, we'll talk about the routing of the board. So stay tuned for those. But that's pretty much everything I wanted to talk about in this section. So thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Welcome back everyone to the layout portion of our buck converter project. So this is the portion of the project where I'm going to go through and share with you any information I think is relevant to doing the PCB design, for this project. So I'll be covering things like component placement, any routing tips I had, general board setup and design guidelines, stuff like talking about the fabrication notes we had, like our layer stack manager, stuff like that. So that's kind of what we'll be going over in this portion of the project. But before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton. And hit the subscribe button for me if you'd like to stay up to date with any future videos in this project. And with that out of the way, let's just jump right into it. So last video, we talked a lot about the general setup we want to have before going into things. We talked about like board logistics, talking about how many layers we want to use, the thickness of each layer, some brief notes on that. Talked about some of the mounting holes, just general board setup tips and notes that I had going into this project before I went into things like routing and component placement. So now that we have all that stuff set up, let's go into the component placement section. So usually whenever you start thinking about component placement, there are a couple you can call like anchor points for your design that you want to consider. And those anchor points are things like connectors and any of your like main chips or ICs that you're going to be using in your design. And I would say it's more so focused on your connectors, because the connectors have a lot more. Usually the connectors have an external constraint put on them. Like, let's think back to our USB charger project that we did on this channel. With the USB charger, we know that the USB port needs to be in a particular location based on mechanical constraints, because that's actually something that's interacting with the user. So like we know it has to hang off the board so much, give so much clearance so that someone can easily plug and unplug it. And then we have mechanical constraints around the rest of the design, like given the orientation of the USB connector, and also just where it is in relation to some of the other components on the board. So that's why it's usually a good idea to start with connectors, because there's usually less place. Usually have they're easy to figure out where to put them, because you have some external constraints to kind of guide you, and then you kind of get this sort of your mind just kind of explodes with all the possibilities. Like, so usually if you're designing a big board with hundreds of components on it, then your mind just you can kind of easily get overwhelmed trying to figure out where to put everything else. And then by starting with the connectors, it gives you a good anchor point, because then, for example, we know that this connector right here, P1, is an input connector, so that means it has to interact with our input feedback resistors, or I say our input resistor divider that controls the V shutdown level, and also interact with our input capacitors, right? So right away we know that our input capacitor is going to be hanging around this section of the board right here. So we start to give ourselves we start to kind of frame our board a little bit, start to give like a rough outline of where we want things to go. And the same thing goes for our output connector, right? We know this is where 5 volts 1 amp is going to be being output from the board. So that means some of our output components are going to have to be at least on this half of the board, right? So at least we have a little bit of board structure already outlined, and we have an idea roughly of where maybe what quadrant of the board these components are going to go in before we have to start considering other things. And some of those other things, which is a good example of, would be like heat dissipation of some certain components, right? So let's take a look at, for example, L1, our inductor, and let's just go to 3D view so it's more obvious. So this component is not only one of the biggest components on the board, so that's already going to take up a lot of, it's pretty easy to figure out where to put it since it's so large. There's not a lot of other options for it. You can't really orient it many different ways, and putting it, one way or another, it really doesn't make that big of a difference. So you're not going to change your board drastically by changing how you lay it out, where you put your L1. And also L1 is going to be dissipating a ton of heat, so it needs to have as much space on the board. So that means I would put it as a higher priority component on there. And so you might place that one in terms of thinking about what order you're placing components as well. Start with your bigger ones that have more constraints on them, that need a little bit more clearance, so that you have the most freedom when it comes to placing those components. So that's kind of how I went about it. Is first I placed my connectors, then I kind of went around and placed L1. I kind of figured out where I want to put that in relation to my output connector, and then kind of an idea of where I thought other components I wanted to put on the board. And then the other main focal point you could think of for a PCB layout is going to be your actual chips or your integrated circuits. So we're talking like U1 right here is a good one to also focus and hone in on, because it acts as sort of a central hub for the rest of the components, because every other component on this board is interacting with U1 in one way or another. For example, we know that, let's just go look at our schematic real quick. So R1 and R3 are going to be on the input side, and we know they're going to connect to the shutdown pin of U1. So that already tells us right away that R1 and R3, and then we have the shutdown pin. So it's pin 4. So that means we know R1 and R3 need to be right around pin 4 somewhere. So that already gives us an idea of where we kind of want some of our other components by focusing in on like U1 here. We already start to constrain some of the areas. We know that R1 and R3 are going to have to be on the pin 4 side of U1. And then the same thing goes for our other input components. For example, like C2, we know C2 needs to be right around, what is that? That pin should be pin 5. So we know that C2 needs to be right around pin 5. Or also I end up putting it near the V external input as well, but also that ends up going to pin 5. So that's kind of what I'm talking about here, is focusing in on these chips or the ICs here, because every other component in one way or another interacts with it. So same thing goes for our output components. I knew that R2 and R4 needed to connect to pin 3. So that means they were going to be I wanted to place them as close to pin 3 as possible. Also, since we were trying to go for a smaller board as possible, that's kind of why I chose that. So that's kind of how I started going about placing the rest of my components. Is what I knew is based on I started with the IC, and I said, okay, I put it down, and then I started slowly. It's kind of a slow process of shifting components around until you kind of get a good idea. I didn't really do any routing until I was comfortable with where every single component was, and I was confident that I could successfully, like, they're all able to be routed. And that's kind of how I went about doing that whole process. Was at first I kind of inched them in, kind of looked at it, and then I also just considered, I kind of moved things around a little bit more, and then I just tried different versions of things, and then eventually I got to something that I was happy with. And that's kind of how I went about doing all the component placement here. Also, if you look at the data sheet, they actually, a lot of times they'll give you sort of a starting guide for your layout example. Right now, this is usually a guideline and not a, for lack of a better term, like the Bible. You don't have to follow this religiously at all, especially because our board has some extra components on it that is not featured in that layout. For example, we have some extra filtering caps on the output. And we also have the resistor divider on the shutdown side. So ours was going to end up looking a little bit different already. And on top of that, we have our input and output connectors. So we already had to start deviating away from the guidelines. But they're still a good tool to use, and it kind of gives you ideas for just performance, and gives us some other ideas that we'll talk about when we're routing. So it's useful to just look at it, take a look at it, refer to it if you need to, but by no means you have to follow this exactly. So the main other things I guess I want to say is pay attention, like the 0603 package size. I think some of this capacitor is like not an 0603. I don't know what, if it tells you, it's a 1206, right? But that's one thing we'll say is pay attention to, is our package choice. And what flexibility it gave us, not only when the routing, we'll talk about the routing in the next video, but with the component placement, how much closer you're able to get some of your components to each other, and just gives you, and that also gives you a lot more flexibility when it comes to the rest of your PCB design. So yeah, that's kind of how I went about doing the component placement for this one. Like I said, this is actually a very simple board, so it was kind of hard to mess up. But as long as your components are all within, as long as your board can be routed, I think this board would be like, it would work just fine the way it is. So that's pretty much everything I wanted to cover with the component placement section of this project. Feel free to drop a comment down below if you have any questions or anything. I'll be happy to answer them. And thank you so much if you made it to the end of this video, and hopefully I will see you in the next one. Welcome back everyone to the PCB layout portion of our buck converter project. So this is the portion of the project where I go over the entire PCB design portion. I go over things like component placement, routing, vias, board setup, and any Altium settings that we might want to have going into our PCB design. Any time of tips and notes that I have when it comes to designing the PCB for our buck converter. Before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton. And subscribe if you'd like to stay up to date with any future project videos I have on this channel. And with that out of the way, let's just jump right into it. So I've already covered the general PCB setup, things like your layer stack, mounting holes, the Altium environment in which you're designing. I already covered all that stuff. Then the last video we talked about component placement and kind of how I went about doing that. And then, so this video, the final part we're going to have is we're going to talk about the routing portion of this project and kind of how I went about routing. So the first thing I guess I want to talk about, and I kind of left off with this last video, is talking about the package size that we chose to go with for most of our components. And you've heard me repeat this over and over again in the calculation section, is make sure you start out with an 0603 package size. And the reason for that is it gives you a lot of flexibility, not only with component placement, but with your routing as well, because you can route between pads. And this is what I said was the minimum component size that I thought you could route between pads if necessary. So thinking about like a 10 mil trace, that's an 0603 is about as small as you can get while still being able to route through route in between pads. And you see we have some larger packages where you can more easily route between them, but anything smaller than 0603, then you're kind of pushing it. So that's a good place to start off. Now, looking at this board, I don't know if the final layout actually included any routing between pads. We did do some routing tricks here where you kind of route underneath your chip and stuff like that, but nothing too fancy. I guess this was a very simple board, and so there's not a whole lot here that we needed. There's not a lot of fancy tricks we use here. So I guess the place I want to start out with is looking at our layout design. And so some of the some of the tricks I pulled from, or ideas I pulled from this layout guideline example, was that they used a lot of copper pores as opposed to individual traces in order to make some of their connections, even with their their non-ground planes, right? So they have looks like a little ground pore right here, and they have a V in and a V out. And since this is not an isolated design, we have one single ground plane for both the input voltage and the output voltage, which is perfectly acceptable. As I said, this is not an isolated topology, so that's okay. And then the other thing I guess I want to note is, like I said, they did a lot of and then other than the use of the ground planes, there's not too much other fancy stuff here. I guess we'll notice that they found it acceptable to route this trace well around, really far, a roundabout way of getting all the way to the output voltage plane, because you would think that they could just stick it here, but I guess they wanted to be extra close to the V out node so that it just keeps a closer eye on when this, because if this this power line is leaving the board, you want to be as close. There might be a slight voltage drop across from here all the way to over there. So you want to make sure that you're monitoring as closely as possible the actual output voltage. So other than that, they didn't do anything too fancy. So I mean, we're just going to keep it simple, stupid, and we'll just kind of go through some of the main things I did. So kind of like them, I used large copper pores wherever I could, especially for some of the power output output connections. So looking at the top layer here, so this is our inductor. So I knew this is actually a really high current connection right here, a really high current pathway. So I knew we want to make our trace as wide as possible, because usually what you might think is just use a really, really fat trace, like 100 mil or 50 mil trace, something crazy like that. But I just ended up using a copper pour, and it worked out just fine. And then you could be a little bit more creative, because we also not only did we have to connect this really high current, this pathway is going through our inductor, but it also has some other connections. We have some filtering caps connected to the same pathway, and then we also have some like this rectifier diode. Then we also have our bootstrap cap. So it just made more sense for me to do like an entire copper pour as opposed to just one trace, because then I have to connect a bunch of other traces. And this will actually also help with heat dissipation, so it'll kind of help our inductor just have a lower operating temperature. And so that's just another benefit of using, that's another reason why you might want to use a copper pour as opposed to just the individual traces. So I ended up doing that for both the input and the output. So I basically just did what they suggested for their output, is I used a large copper pour on the output. And it's the same exact reason, because we have all these capacitors we have to connect to the output node, or the output net, and then we also needed to place a connector there as well. And to me, like I said, instead of just routing a bunch of individual traces here, it just makes it, I think the filtering caps can do a much better job of filtering this entire plane as opposed to trying to filter the individual traces. They kind of work together, so to speak, and I think that works a little bit better. And then also I think that routing this, being able to route this trace up and around was made to just, it looks a little cleaner whenever you can use like a nice copper pour on the output. And then you can also get just a lower impedance connection all the way to your output voltage, which in this case, I guess we could honestly have moved, since this is our output voltage right here, we could have actually moved this all the way up to somewhere like right here, because it would keep a closer eye out on, since this doesn't need to be connected to VCC ground, we can just keep a closer eye out on our, because the whole point of this copper trace is to keep an eye out, is to more closely monitor our output voltage. And so like if you look at the layout example, they have this thing routed all the way out and really close to your V out. Well, with this case, it'd be like a mounting hole or a test point or something. But in our case, they routed all the way around. We want to route all around to the output connector, which is where our voltage power line starts to leave the board. So that actually might be better suited for being routed just all the way, and we can even put it like right there or something like that, and then just get rid of that right there. So something like that might have been more appropriate actually. So that's kind of what you can do there. And then I just think having really good solid connectivity for our like our output voltage just helps with our connector. And then other than that, there wasn't too much other stuff. Like I did a little bit of fancy routing techniques. If you look right here, I know our input current is not going to be too high, at least especially compared to our output current, because our input voltage is so much higher. And then so I ended up doing some nifty tricks where you can just route underneath the chip. So looking at the mechanical layer, so this trace is going underneath our buck converter chip, and the same thing goes for this chip. And just so you can kind of hit these pads from all angles and have a better ground connection. As I mentioned, this is a 2-layer board, so we have the bottom plane ended up being mostly a ground plane, I think, pretty much entirely a ground plane. So that just, because I wanted a nice solid connection because if you look, we have all of these points across the board share the same ground, right? So I just want to make sure I have a really good connection to ground, especially from our input and output. And so I just felt like a large copper pour here would have done the job for that. And so that's kind of what I ended up doing there. So that we have these two grounds connected. Then it's really easy just to shoot straight to ground, like we're talking about right here. Like trying to get to ground here, we're sort of trapped. Like this trace was already being routed here. We could have done something crazy where we like routed through here and then like went around town and like down here or something. But that would have just kind of gotten in the way of our inductor setup right here. I wasn't really comfortable with that. And I guess I could also gone like way around here or something like that, but it just seemed it's a shorter trace and have a nice solid ground connection with a via right here, and I thought that kind of did the job just fine. But other than that, it was just pretty typical stuff. I tried to use thick traces if there are any type of high current pathways that we were following. So this one, for example, let me see, I think I'm in metric right now. So this is a 25 mil trace right here. So this is our rectifier diode. So I knew that was having really high current. So I tried to either use a big, really thick, really wide copper pore if there's high current, or I try to use an extra thick trace. Same thing goes for our input. If I had the extra room, I just went ahead and did a nice thick trace, and that's kind of my thought process behind all of that. So other than that, that's pretty much everything that I wanted to cover for the routing portion of this. Like, it wasn't too complicated. If you have any questions about the routing portion, just let me know, and I will be more than happy to answer those questions in the comments below. And other than that, yeah, thank you so much if you made it to the end of this video, and hopefully I will see you in the next one.